So we just started talking about waves. So we're going to kind of go into some graphical representation of waves and the differences between the kinds of waves that we're going to talk about. Now, we don't talk that much about light in this course, but you do need to know that it's a wave. So this question asks, what's the difference between the waves coming from a tuning fork and an electromagnetic wave or a light, like this one right here? The second part asks you to represent it graphically, and the third part says, why is the sound produced by a tambourine different from the sound produced by, say, a bass drum? So the first part, let's talk about the differences between a tuning fork and a light source. A tuning fork creates a kind of wave called a longitudinal wave. And a longitudinal wave is one where the particles vibrate, the vibration happens parallel to the direction of the wave propagation. And I know Professor Hafner's probably talked to you about this a lot, and he will again. But when you have a longitudinal wave, you can kind of think of it like a slinky. These vibrations happen in the same direction as the wave is traveling. Okay? The other thing about a tuning fork is that it's a mechanical wave, and a mechanical wave just means that it needs something to travel through. In this case, it's vibrating the particles in the air, right? And in this case, it's vibrating the coils on the slinky. When you talk about light, it's what we call an electromagnetic wave. So what's vibrating are things that we're not really going to talk about in this course, but the difference is that an electromagnetic wave can travel through a vacuum. It doesn't require a medium. And in an electromagnetic wave, the thing that's vibrating actually travels like a string or a water wave. The vibrations are perpendicular. They're in a different direction than the direction of wave propagation. So let's look at the graphical representation. In a longitudinal wave, and we can think about the slinky here, what is traveling is the density of the particles, or in this case, the coils. So if you look at the density changing, you can just put dots to represent it, okay? Imagine with the tuning fork that this is particles of air. You plot density versus distance, and it looks just kind of like a sine wave. The parts of the wave that you need to remember is that the densest parts are called compressions, and the least dense parts are called rarefactions, which is a fun word. If there was no wave traveling on it, and it was just stretched, that would be called equilibrium, so it passes that point at some point in time. And the wave looks exactly the same if you plot things a little differently when you're doing a transverse wave. It looks just like a sine wave, but we know that this is actually a wave traveling, right? Think about a wave at the beach. So the top of the wave, the furthest distance from displacement in the positive direction is called a crest. The furthest distance in the negative direction is called a trough. And from compression to compression, or from crest to crest, that's called a wavelength. There's way more involved, like this height is called the amplitude. But we're going to get to all of that, so don't get too overwhelmed. The last part of the question asks, why does a tambourine sound different than a bass drum? And that's kind of a really cool question. The difference is the size of the thing creating the object. Here, we've got less room to bounce that skin on the tambourine. Here, we've got a lot more room. In fact, you've got so much room, you've got to use a pedal, right? So in this case, the sound is relative to the size. A smaller size is a higher frequency, and a larger size is a lower frequency. So welcome to thinking about waves, and we're going to talk a lot more about it. So I hope this gives you a little bit of an idea where we're headed, and I look forward to it, hopefully as much as you do.